Hi, this is the worked out examples for Module 2. 7.11 is a problem set from the book Castellan. Changes in state at constant volume, example 7.1. Calculate the delta U and Q sub V for the transformation of 1 mole of helium at constant volume from 25 degrees to 45 degrees centigrade. So we just need to calculate the change in the internal energy and the heat produced during a constant volume process while 1 mole of helium is heated under constant volume conditions from 25 to 45 degrees centigrade. So now we use equation 7.19 from the textbook, and we can then write delta U as integral CV dt. So change in the internal energy of the system as we travel from temperature 1 to 2 is the integral under the heat capacity curve over those limits. So CV is the heat capacity under constant volume conditions of the sample, and dt the infinitesimal change in the temperature. Since this process is at constant volume conditions, we're using heat capacity under constant volume conditions. So integration of this process equation gives us integral CV dt equals to 3 half R T1 to T2 dt. That's because CV is simply equals to 3 half R. And so this is something we need to keep in mind because it's 3 half of R, and for helium or any ideal gas for that matter. And so 3 half R integral T1 to T2 dt, and so 3 half R delta T after integration. Delta T is 20 Kelvin, and therefore we can substitute the values here and then get the numbers. So QV of course is equal to delta U because this is a constant volume process, and so 3 half R 8.314 joules per Kelvin mole, 20 Kelvin. So Kelvin and Kelvin cancel away. Joules per mole will stay behind. And so this is a simple trick where you don't worry about the units until the last minute. So substitute all of them and then make the conversions necessary to cancel them off. This is what I promised to tell you in the previous module. So that will be 250 joules per mole. In this next slide, we are doing example 7.2. So you have silver with a heat capacity under constant pressure conditions of 23.43 plus 0.00628 T, where T is the temperature. The Cp is given in joules per Kelvin mole. So that is, Cp in this case is expressed explicitly as a function of temperature. Remember, in the case of helium, it's independent of temperature. But here, it's defined as a function of temperature. This is experimentally determined value. So now calculate delta H if we heat 3 moles of silver in the solid form from 25 degrees centigrade to its melting point, which is 961 degrees centigrade under 1 atmosphere pressure conditions. So same essentially as the previous example, except that instead of helium we have silver. Instead of constant volume we have constant pressure conditions, and instead of Cp being a constant we have Cp as a function of temperature explicitly given to us. So using the same equation now, integral Cp dt instead of Cv dt, insert temperature 1 to temperature T2. Instead of delta U you have delta H because this is a constant pressure process. So that is integral of Cp as a function of temperature dt. The integral sign is missing on the right hand side of it. 23.43 plus 0.00628 T dt, integral of that. And so then you get delta H is equal to the integral 23.43 T2 minus T1, that is your first term in the parentheses, and 1 half 0.00628 T2 squared minus T1 squared, that is the second half after integral because T dt is T squared, right, integral. So that's what we get, and we put this units into it. The joules per mole is the units for the entire entire for both terms together. And so the Kelvin cancels away because you have temperature in Kelvin there. So T1 is given, T2 is given, T2 minus T1 is calculated. And so then substituting into delta H, you get these values. And 936 is the T2 minus T1. And then T2 squared minus T1 squared. And you can take a calculator and compute the numbers. And all these numbers now are in joules per mole, because everything else is taken care of, cancelled away. And so you get the end result, 26,430 joules per mole. So as we doing this stuff, what we're doing is that you substitute the proper units in the end of the equation, towards the end of the equation, and convert if necessary, so that a lot of these units get cancelled away, and cancel them very carefully, so that you don't miss any. And then a very good habit, and this is one of the tips I want to tell you, is to check if your numbers are reasonable. For example, delta H has a certain value. Okay, so what is delta H? It's the change in the enthalpy. Now, when you carried out this process under constant pressure conditions, so we use Cp, that is correct. We use delta T or integral dt, that is correct. And substitute the numbers T1, T2 and squared them and all that. So now units are also correct because this joules per mole. That's what the delta H is supposed to be for the process. And now we need 3 moles of it, not just 1 mole. So 3 moles of it. So you simply multiply it by 3 moles, this value of delta H, and then you get the change in the enthalpy for 3 moles of the substance. So then moles and moles cancel away, you get joules. So in the end, the result is energy in joules. So this ought to be correct. So this is something you need to think about as a tip, whether the final answer makes some sense to you. So it has certain number and it has certain units. So are the units correct? That's the first thing you want to check. So enthalpy change in joules, that's perfectly fine. Either it has to be joules or joules per mole. Since we are using 3 moles of the substance, it should be in joules. If it is 1 mole, then joules per mole. That's the idea. So that checks out correct. And so if the end result were to be joules per Kelvin or Kelvin per mole, then we know that we made some error somewhere in the middle, and so we need to go back and make sure that is corrected properly. So most of the time we don't do that. We simply look at the number and then move on, and without realizing that we may have made a mistake somewhere. So that's a very good thing to check the answer against your understanding. Does this make sense? Good question to ask. So this is example 7.4. Using the values of enthalpies of formation, standard enthalpies of formation, given in this table in the book, calculate the heat of reaction for this particular process, iron oxide plus hydrogen going to iron plus water. So the first thing we need to do is make sure we balance the chemical equation. And this is one of the reasons we balance chemical equations. We probably never taught you that. The reason to balance is that number of moles of each element on one side should be the same as number of moles of the element on the other side. The matter can neither be created nor destroyed. In this particular case, elements cannot be destroyed or created in a regular chemical reaction. So that's the reason we balance the chemical equation. So 1 mole of iron oxide in its standard state, which is a solid, plus 3 moles of hydrogen in the standard state as gas, reacts and produces a solid iron metal in a solid form, plus 3 water molecules or 3 moles of water in the liquid form. So these are the states that the products and reactants are specified for our reaction. So now all we need to do is use the data in the table and make substitutions. So what we find from the table is that the delta H formation of water in its liquid state is given, and delta H formation for an iron oxide in solid state is given, These are the kilojoules per mole. Negative numbers mean that the reactions are exothermic. The system is losing heat and into the surroundings. So these are exothermic reactions. So then delta H for the reaction can be calculated as the enthalpies of products minus enthalpies of reactants. So which I have written explicitly here. So 3 moles of water. So 3 times minus 285.830 kilojoules per mole plus the heat of formation of iron in its pure elemental state in the solid is 0 by definition. So that is plus 0. And of course 2 moles of it, so 2 times 0, you can do that if you want, minus that of the reactants. So 1 mole of iron oxide, so minus 824.2 kilojoules per mole, minus that of hydrogen in its standard state. A gas phase is the elemental, it's a molecular form, and so it is enthalpy formation of pure hydrogen gas is 0 by definition, and therefore we have value 0 times 3 equals to 0. So now you sum all the numbers, they're all in kilojoules per mole, and so you get minus 33.3 kilojoules per mole as the heat of reaction. All right, so the last example is 7.5. This is the heat of combustion. So you may have done this experiment in the physical chemistry lab. Take benzoic acid and then you react it with oxygen completely, and you get carbon dioxide plus water. So benzoic acid is in the solid form, C6H5COOH. The oxygen, of course, in the gaseous state, and carbon dioxide is in gas state, and the water is produced in the liquid state. Initially, the water may be produced in the vapor phase, but you wait for it to condense at room temperature back to liquid form. So that's what we do in the physical chemistry bomb calorimeter experiment. Now we need to again balance the chemical equation for reasons described previously. And so we have 1 mole of benzoic acid reacting with 15 by 2 or 7.5 moles of oxygen to give rise to 7 moles of carbon dioxide plus 3 moles of water. All their states are specified. So this is very important. Without specifying the states, we won't be able to calculate the heat of combustion. So in this reaction, number of moles of product, number of moles of reactants are different. So number of moles of product is 7 moles of carbon dioxide plus 3 moles of water. But when you calculate QP and QV here, that's what the intent of this example is. And then we only consider the gases, number of moles of gases only. So because we're calculating the change in the volume. What will the change in the volume when the reaction proceeds? So number of moles of products minus the number of moles of reactants. If that is 0, then there is no change in the volume. If the product moles are greater than the reactant moles, then there is an increase in the volume. But if you keep the volume constant, the pressure will increase. And similarly, if the number of moles of product is less than that of the reactants, then the volume decreases. But if you keep the volume constant, then the pressure should decrease as well. And so we are trying to figure out the relationship between QP and QV. That is heat of combustion under constant volume conditions versus heat of combustion under constant pressure conditions. So delta N for this reaction is equal to 7 moles of the product, carbon dioxide, minus 15 by 2 moles of oxygen goes to minus 1/2. Therefore, there is a decrease in the number of moles of the system, and so there is a decrease in the volume, or if you keep the volume constant, there should be a drop in the pressure. And the experiment is carried out at 298.15 Kelvin. So that is given. So equation 7.73 gives the relation between QP and QV. QP is equal to QV plus delta N RT. Delta N is the change in the number of moles as the reaction is completed. R and the T are same as before, as we know. So QP is heat of reaction under constant pressure conditions, and QV is the heat of reaction under constant volume conditions. QV so this relationship between QP and QV, it can now be translated by substituting the numbers into it, delta N, R, and T. So QP equals to QV minus 1,239 joules per mole. Kelvin and Kelvin cancel away, and so we're left with joules per mole. And so the reason to consider only number of moles of gas is I've explained to you, and that's simply because the volume depends on the of the system depends on the volume of the gas and not the volume of the solids or the liquids, because they occupy very little volume per mole compared to the gases. And so we simply neglect the volume of the liquids and solids in computing these things. So that is a good approximation.